So good afternoon, everyone, and welcome to this lecture. This is lecture number 2, and we are dealing with magnetic effects of current. If you remember, in the previous class, we had gone and seen what? Seen the where is that? Seen the beginning of this Biot Savart law. We had seen what do you mean by a current carrying element, and we had also seen how we can find out the magnetic field due to a current carrying element. The small magnetic field that this current carrying element creates is given by this formula, which is on your screen: mu naught by 4 pi I dl sine theta by r square. This is the scalar formula, and dl cross r gives you the direction of magnetic field, and the direction of magnetic field is perpendicular to both dl and r. In fact, it is given by something known as the direction of this is given by something known as RHT rule. Do you know this RHT rule? Yes? Anyone has idea about this RHT rule, which gives something about the cross product? Anyone? No one knows it? No one knows it? Never heard this RHT rule? This RHT is known as the right hand thumb rule. Now this gives the direction of cross product of two vectors. If your first vector is your A vector, so your right hand, this is your right hand, you put your right hand thumb. So you put your first vector in the direction of the, you put your thumb in the direction of the first vector. Right hand thumb. So this is the thumb. It goes in the direction of the first vector. Your palm will go in the direction of the second vector. So this is the first vector and this is the second vector. Then if you turn your fingers, see these three are perpendicular directions. If you turn your fingers by 90 degrees, this will give you the direction of the cross product. Right hand thumb rule. First vector, second vector, cross product. 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 Do we understand? How do we use it? Right hand thumb rule. It gives the direction of magnetic field by the cross product of dl cross r. Now in the diagram, if you see, your dl vector is in the plane of the board, or right now on the plane of my tablet. So dl is here. The r vector is like this, it is at an angle. So dl cross r, if you turn your fingers, the direction of magnetic field goes inside. The inside direction is denoted by the inside direction is denoted by cross. Cross means something is going away from you. Dot means something is coming towards you. Cross and dot convention. Do we remember? Do we know this cross and dot convention? Dot means something is coming towards. You see the dot, it's from the arrow. If someone has hit an arrow towards you, you will see the point of that arrow, head of that arrow. The head of the arrow is your dot, and your back portion of the arrow is the cross. So if you see cross, that means something is going away from you. Do you understand how I found out the direction of magnetic field with the right hand thumb rule? Do we understand this? Yes or no? Right hand thumb rule gives us the direction of magnetic field. Here this mu naught We did not discuss this mu naught. What is this mu naught known as? What is this mu naught known as? Anyone? What is this mu naught known as? Mu naught? It is known as the absolute permeability. Epsilon naught, what? Permittivity. This is permeability. Absolute permeability of free space or vacuum. It is a constant, and the value of this constant mu naught is 4 pi into 10 raised to the power minus 7. Now there are different ways in which you can write the unit of mu naught. You can write it as Weber per ampere meter. You can write it as Henry per meter. We will understand what is this Henry. Henry per meter. You can write it Newton per ampere square. You can write it as Tesla meter per ampere. Different ways in which you can write the value of mu naught. 4 pi into 10 to the power minus 7, any of these units, whatever you want to use. Also, I have told you one more thing in the previous class. Mu naught into epsilon naught is 1 by c square. Do we remember this? Okay, so that is what we have did in the previous class, and we are obviously starting our this class from here. Remember, this Biot Savart law gives us the magnetic field created by a very small segment, a current carrying element of the wire. Now what we have to do is, obviously the wire that we are going to get will not be a very small element. It would be a long wire carrying current. It would be a long wire carrying current. Now, to find out the magnetic field due to a long wire which carries current, we will have to break the wire into small portions and then find out the magnetic field. So you can write the next heading, magnetic field due to a straight wire. Magnetic field due to a straight wire. And how do you find the magnetic field due to a straight wire? Well, we are not going to find it out because it is of no use. What we are going to do is try to understand the formula once we get it, and we will try to use and utilize this form in whatever ways that we can. So what we
Sir,
have?
one show previous slide.
What we have to write in the previous slide? Okay, this is the previous one. Once you are done, let me know. Okay, then we're going to use the formula for that current carrying element, and we can find out from that current carrying element by integrating. We can find out the value of magnetic field for a straight wire. The current in the wire, as you can see, is I. So what things will be given to you normally? You will know what is the current in this wire. The second thing you will know would be the distance of this point, the perpendicular distance of this point from the wire where you have to find out the magnetic field. Two angles would be given that will tell us from where to where the wire extends. Now remember, we have seen the similar type of diagram in calculating the electric field due to a wire. Do we remember that? Do we remember that diagram? This is the same diagram, but now we, instead of finding out current, instead of finding out magnetic, instead of finding out electric field due to a line charge, Here we are trying to find out the magnetic field due to a current carrying wire. The value of magnetic field will be given by this formula, and this formula looks similar to what we have already done. The magnetic field due to this wire will be given by this formula, mu naught by 4 pi r, mu naught by 4 pi r into I, which is the current in the circuit, not the circuit, current in the wire, sine of theta 1 plus sine of theta 2. And if you could recollect, it looks similar to what we had done in the chapter on electric field. You can go and compare the two equations. The only difference here is this magnetic field is going into the board, and that electric field was in the plane of this board, and it had two components, x and y. This is the magnitude of the magnetic field created by a straight long wire at a point at a distance r from the wire. You'll have to remember this, because wherever you see a straight wire, we will try to apply this formula and try to convert the figure, whatever type of figure is given to you, we'll have to convert this into this standard figure, and then we can apply this formula. This was the magnitude of magnetic field. You also have to find out the direction of magnetic field. So how will you find out the direction of magnetic field? You put your thumb in the direction of current. It's going like this. Then you put your fingers in the direction of point A. So as you can see from the board, my thumb is going in the direction of current. My palm, I am trying to point it in the direction of A, and you can see where my fingers curl. My finger curl into the board. Since my finger curl into the board, the direction of magnetic field at this point will be, oops, wrong color. The direction of magnetic field will be into the board like this. Do we understand this? Do we understand this? Are you able to understand the direction of magnetic field? Yes or no? You able to understand the direction of the magnetic field? Yes or no? If the point A is on the right hand side, the direction comes into the board. If the point A was on the left hand side, then what would have happened? Let us suppose the point A was here. This was the point A now. Point A is here. What would be the direction of magnetic field at point A if it is on this side? If it is on this side, point your thumb in the direction of current. Now the point comes on this side. You turn your fingers are coming towards you. Therefore, the direction of magnetic field on the other side will be dot, and it will be coming towards you. Do we understand this? Yes or no? Do we understand this? Yes or no?
Sir,
In fact, as I told you in the previous class, magnetic field is in a closed loop. It has to be moving in a loop. How it is moving? This, let us say, is your wire. Look at me, don't write. You can write it after on. If this is the wire and this is the current in the wire, I hope you can see this. Make it big. This is the wire and this is the current in the wire. Current goes like this, top. So I put my thumb in the direction of current, and then I move my palm to any point where I want to find out the magnetic field. At this point, the magnetic field will go like this. At this point, it will go like this. In fact, if I turn my fingers, if I turn my palm everywhere around, the magnetic field will be moving in a circle like this. Do you understand this? The magnetic
sir,
field will be moving in a circle like this. If I put the current like this, so current is going towards the screen right now. So I put my thumb in the direction of current. This is the direction of current. I put my thumb in the direction of current, and you can see my hand will curl like this. In that case, the magnetic field will move in a circle like this. Do you understand what I'm saying? This is how you can find out the direction of magnetic field. If this current was coming towards me like this, then I will put my thumb in my direction, and then you will see the magnetic field will go like this. Do you understand what I'm saying? Do you understand what I'm telling you?
Sir.
That is how you can find out the direction of magnetic field from the direction of current, depending on where you are finding out that magnetic field. I hope everyone understands this. If you understand magnetic field ka direction, well, that is the only thing that can trouble you in this particular chapter, because rest all is pretty damn simple. Just have to remember three standard results and you are done. We get this? Yes or no? Yes
Sir.
or no? Have you noted this down?
Yes, sir.
Pakka, sir?
Yes,
Shall
sir.
we move ahead?
Yes, sir.
Now, if you know the magnetic field due to a straight wire, you can use this to get some standard results, some special cases. Special case number one, magnetic field due to an infinite wire. Magnetic field due to an infinite wire, and I'll try to post the same diagram, and then I will just make that thing as infinite. Same diagram, but now the wire has become infinite. What difference does it make? If the wire becomes infinite, it does not have any end point. This point P does not exist. The wire just keeps on going like this in this direction. The wire is coming from infinity in this direction. Do we understand infinite wire? So the same formula they can apply for infinite wire. For infinite wire, you just have to put the values of theta 1 and theta 2. What will be the value of this angle theta 2 for an infinite wire? What will be the value of theta 2 for an infinite wire? The wire extends till infinity. No one knows it. Well, the value of, yes, I think your mic is not
Yes,
working.
sir.
You don't have to come. Just sit there, beta. I don't want you to be trouble. If your mic is not working, just stay there. This angle would be 90 degrees for an infinite wire. And similarly, your green angle, theta 1, infinite wire coming from infinity, it would be 90 degrees. You just put the value of theta 1 and theta 2 as 90 degrees in our original equation. What was the original equation that we had? The original equation that we had was B was equal to mu naught I by 4 pi r into sine of theta 1, 90 degrees, plus sine of theta 2, which is also 90 degrees. Sine 90 plus sine 90 is 1 plus 1, 2. So you get the value of magnetic field for an infinite wire as mu naught I by 2 pi r. This is the result, and this is just a special result of a special case where the wire comes from infinity and goes to infinity. This is the magnitude. Remember, to find out the direction, you again have to do the same thing, ding, 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 and all this. So you can see that the magnetic field at this point, wrong color, the magnetic field at this point will be going into the plane of the board like this. Do we understand this? Yes or no? No, yes.
Sir.
This is the magnetic field due to an infinite wire. We have done nothing extravagant. We have just put the values from the standard result and got our answers. Noted this down?
Done, sir.
Then you can I can make large number of cases. I'll just make 2 or 3, the most occurring ones, and then probably you can understand. Semi-infinite wire. Semi-infinite wire. At the end of the wire. Basically, what I mean to say is, I have a wire like this. It extends to infinity only in one direction, and in the other direction, the wire has an endpoint. So this is the point P, where we are supposed to find out the magnetic field. The current in the wire is I. This distance is definitely given as R. This is again a special case of the previous one. What will be the magnetic field at the point P? And the answer would be, what will be the magnetic field at point P here? The magnetic field at point P will be mu naught I by 4 pi R. One angle has become 90, theta 2 has become 90, theta 1 has become 0, so sine 0 plus sine of 90. And I get this result. The magnetic field at this point, semi-infinite wire, at the end of the wire will be mu naught I by 4 pi R. Simple result. You just have to remember one formula, and from that one you can find out all these results automatically. Magnetic field due to a semi-infinite wire in this particular case, where you find a magnetic field at the end point, or you may call it the starting point of the wire, whatever you want to call it. Have you noted it down, bacha?
Sir.
Okay. Shall we move ahead?
Yes, sir.
You can make a lot of cases. I'm trying to restrict myself to only those cases which I have seen come a lot of times. Again, I have semi-infinite wire, but the point is not at the end. So in between, the point is somewhere in between. The point is somewhere in between. Now, what do I mean by in between point? So basically, I have a semi-infinite wire, but the point P is here. Point P is here. The point P does not lie at the end of the wire. Wire starts from this point A, and then it goes till infinity. But the point P does not lie at the end. Point P lies somewhere before the end. And let me call this angle as theta, or theta 1, or whatever. The distance is definitely equal to R. Can anyone tell me? You can take it as a question. What will be the magnetic field at this point P due to this wire? Yes. What will be the magnetic field at point P due to this wire?
Mu naught I by 4 pi r into 1 plus sin theta.
Mu naught I by 4 pi r. One angle is 90, the other angle is sine theta. So your answer would be like this. That is the correct option. Again, this is just the magnitude. The direction again would be found out by the right hand thumb rule, and the direction even in this case would be inside the board. Do we understand this? Yes or no? This is semi-infinite wire at a point which is lying somewhere in between. One more case we can do. Case number 4. Semi-infinite outside the wire. Have you noted down that case? Have you noted down that case? Okay. Let me know once you are done.
Done, sir.
Done, everyone?
Yes, sir.
Then the next case is semi-infinite wire outside the wire. Oh, what it means? It's better to draw it than to tell you the meaning of it and what has happened here. Things have come to a close. Semi-infinite wire outside the wire is what we are trying to discuss, and diagram looks like this. So we have a wire which is extending till infinity. It starts from this point A, it goes till infinity. The current is I, but the point is not here. The point is here, point P. The distance you must understand will always be given by R.
Please show previous space, sir.
This angle, let me call it
Sir,
as theta. This angle, let me call it as theta. No, not this angle. Which angle should I call as theta? Not with the horizontal, I have to call it with the vertical. I have called it with the vertical. This angle, let me call it as theta. If this is the case, the point lies outside the wire. What will be the answer in this particular case? The answer in this particular
sir,
case will be mu
sir.
naught I by 4 pi 1 minus sine theta. So note this down. Once you've noted this down, then you can note it down. There's nothing.
Sir,
Once I move forward and I'm doing something, please don't disturb me. Do we understand this? So if you have missed something, you can just leave some space and you can come back at a later time, okay? So this is the case where the point lies outside the wire. Instead of 1 plus sine theta, it becomes 1 minus sine theta. So first note this down, take a deep breath, we'll come back to that. Leave some space, you can leave some space, right? So once you are done with this, let me know. I'll take you back to that one. You can note it down. Now, if you have more than one wire is bent in different forms or different shapes, then how will you find out the magnetic field? So you can apply superposition. of magnetic field. It's valid for any type of vector. If you have magnetic field due to more than one wires, what will be the net magnetic field? The net magnetic field will be B1 plus B2 plus B3 and so on. You just need to add them vectorally. So basically I can write it summation of BI. So the net magnetic field at any point in space due to more than one wire is nothing but summation of BI. That simple as that. I hope you understand this. Have you noted this down, everyone?
Sir.
Then we have this point. You have two infinite wires separated by a distance of d, and you have a point P which is exactly at the middle of these two wires. The question is very simple. What is the magnetic field at point P? What is the magnetic field at point P? I'll give you 2 minutes to give me the answer. So, how are we supposed to solve this question? The distance from both the wires is same. The current in both the wires will be same, is same. Both the wires are infinite. So both the magnetic field would be same. We just have to see whether they are getting added up or whether they are cancelling each other out. If I look at this pink wire, and if I want to find out the direction of magnetic field, the pink field, the wire is like this. If I point out my finger, the magnetic field will be going in the inside direction due to the pink wire. We all understand this? Due to the pink wire, the magnetic field is going inside. If I now look at the green wire, due to the green wire, the magnetic field will be coming outside. Both the magnetic fields are of same magnitude, and they are one is going inside and the other one is going inside. So one is plus k, other one is minus k. The net magnetic field at point P will cancel out and your answer would be 0. Do we understand this? Yes or no? We understand this, that the answer is 0? Yes or no?
Yes, sir.
Okay. Now if I would have changed the question and if I would have made one of the wires in the opposite direction, the current in the opposite direction, then what would be the answer? So I make the diagram again. I think this is a straight line, should be. I make the wires having current in the opposite direction. This wire has current I in this direction. Both the wires are infinite, remember, and this wire has current in this direction. Same question, the distance between the two wires is d. Now can you tell me what is the magnetic field in this case? The first case, the net magnetic field is 0 because they are cancelling each other out. Can you give the answer in the second case? What is the magnetic field? I'll give you 2 minutes to give me the answer. Think about it, use the formula and get the answer. How are we going to solve this? We understand that both the wire are same, both the magnetic field would be same. The field due to the pink wire, will be going in the inside direction. The field due to the green wire also will be going in the inside direction. I hope you have understood this. Both the magnetic fields are same in magnitude, infinite wire. So the net field becomes 2 times of single field. So 2 into magnetic field due to an infinite wire. You just have to put the formula mu naught I by 2 pi r was the formula. 2 pi r, 2 say 2 will cancel. Whatever is left is the answer, and the direction would be cross. Cross means it is going in the direction inside of the board. If you want to write it in the vector form, you can write B net. Net magnetic field is mu naught I by pi. Remember R, the value of R is D by 2. I forgot to mention that this D is the distance between the two wires. R is D by 2. So don't forget to write it as D by 2. So your answer will be 2 mu naught I by pi D minus K. I hope all of you understand this. Yes or no? How I've written this? Everyone understands? Yes or no? Thumbs up will give me more confidence that we are in the same class. So this is how you have to find out magnetic field due to wires if you have more than one wire, 2 wire, 3 wire, 4 wire, and so on. Do we understand this, everyone? Yes or no?
Sir.
Okay. Remember, there are infinite number of questions that are possible. We cannot do infinite number of questions, so I'll try to restrict them to not bare minimum, but because see, I can make infinite number of configurations. So we cannot do infinite questions. So what I am going to do, I'm going to do some selective ones. So this is the first one. And I will, in one diagram, I will make 2 or 3 so that you can try those 2 or 3 questions at the same time. In all the cases, the wire is coming from infinity and going to infinity. The point P is here. And all these distances are R, and R. You have to find out the magnetic field at point P. This is diagram number 1. This is diagram number 2. This distance is R, this distance is R. And let me make one more. This is going to infinity, this is going to infinity. Point P is here. This distance is R and this distance is also R. In all the three cases, you have to find out the magnetic field due to the wires. These are the three cases that I have made. In all the cases, current is I and the distance is R. Everyone understands the question? In all the cases, wires are coming from infinity and wires are going to infinity. I'll give you 5 minutes. Do you want me to solve any one of the questions or you can do it on your own? Okay, let's see. I'll give you 5 minutes and then I'll solve them. So how are we supposed to solve this? Let us now, everyone please concentrate on the board and see how it is done. Let me call the wires. This is wire AB, this is BC and this is CD. This wire AB, let me call this as the pink wire. Now for this pink wire, let me find out the magnetic field. Let me call this as B1. What will be the value of magnetic field B1? Let me write it in the form of vector so that I don't make a mistake. What will be the value of B1?
Mu naught I by 4 pi r into 1 plus sine theta.
What is that sine theta equal to? If you just write sine theta, there is no theta given in there. You cannot write it as sine theta. You must find the value of sine theta, otherwise what we have done. You have to join this by this and you just have to find out the value of this angle. How much is this angle? This has
45.
got, yeah, so don't call sine theta. This is 45. How much is this angle? And how much is this angle? You must know all these angles. Yes. All the angles are
45.
45, 45. And this is also 45. Now let us go back and see the value of B1. What is the value of B1? Mu naught I by 4 pi into distance is R. 1 plus sine 45 is 1 by root 2. Yes or no? Yes or no? Do we get this? Yes or no? Okay. And what is the direction of this magnetic field? Is it coming out or it is going in?
In.
It is coming out. Please find out the direction. It is coming out, so it is along K. The current is downwards, remember. Let us now find out the magnetic field due to this green wire. What is the magnetic field due to this green wire? Again, I will have to put the formula for wire. B2 mu naught I by 4 pi, distance is R. What are the angles for this wire? If I compare it from the standard figure, what are the angles that the wire makes with the point P? It is 45 and 45. Yes or no? So it is sine 45 1 by root 2 plus sine 45 1 by root 2. And again I find the direction. Current is here. Current is here. Point is here. This field is coming out. All the fields are coming out, in fact. We will see. So this is along K. Then we see this blue field. And if you understand the symmetry, the blue field will be same as the pink field and it will be coming out. If you don't understand it, you can write it B3. B3 will be equal to mu naught I by 4 pi R into 1 plus 1 by root 2, and that will also be going along the K axis. K axis means the positive Z axis that is coming out. So what is the net magnetic field? You will have to add up all these three fields and you will get your answer. Do we understand this? We understand this, everyone? Okay. From here, let me move on to this question, question number 3. In question number 3, I have this wire, wire number 1. Let me call this as the pink wire. What is the magnetic field due to the pink wire? B1. Now this pink wire and the first pink wire, as you can see, are same. If you understand the first wire, you can write the magnetic field due to this wire also. It will be mu naught I by 4 pi r into 1 plus 1 by root 2 sine 45 along k. Do we understand this, everyone? Yes or
Yes,
no?
sir.
Then the green wire is straight away going like this. You have to find out this angle. This angle will be coming as 45. The other angle will also be coming as 45. The direction of field will be coming out. So both the fields are getting added up. If you look closely, both the fields are also same in magnitude and same in direction. So if you find out any one field, you can just add it up or multiply it by 2. Do we understand how I got the answer for this one? Yes or no?
Yes, sir.
I don't see anyone. Do we understand how I got this? Okay, okay. Fine. Then remains the third wire. Now, let me make it as pink. Now, this pink wire is same as all the three pink wires. The point is same. So, the magnetic field due to this pink wire is also going to come as same. Let me write it once again. Mu naught I by 4 pi r into 1 plus 1 by root 2, and the direction will be k. No points of guessing this one. Now, when you think about this blue wire, the wire which is blue in this diagram, what is the magnetic field created by this blue wire at the point P? What is the magnetic field created by the blue wire at the point P? Point P lies directly behind the blue wire. Whether it lies directly behind or it lies directly in front, the magnetic field, both angles would be 0 or 180. The magnetic field would be 0. So this wire is not going to create any magnetic field at point P. Do we understand this? Do we understand this?
Yes, sir.
Now, to find out the magnetic field at point P due to this wire, which is the green one. Now, this is the only wire that is left, the green wire. But this green wire is not in the form of the formula. The formula is mu naught I by 4 pi r. R is the perpendicular distance. Here, this r which is given is not the perpendicular distance. Do we understand this? So, what you have to do is drop a perpendicular on this wire. So, this is the perpendicular that I have dropped. This is complete match. Both these angles would be 45 degrees. So I got both the angles as 45 and 45. The length of this perpendicular that I have dropped from the right angle triangle, you can find out that the length will be r divided by root 2. Yes or no?
Sir.
Once we have converted this wire in the original form, now I can apply the formula. The magnetic field created by this wire, green wire Bu2, will be equal to mu naught I by 4 pi. Remember, the value of r is not r, it is r by root 2. R by root 2. Both the angles are 45. So 1 by root 2 plus 1 by root 2. The only thing that is left is the direction. The wire is like this. The point P is here. The direction comes right towards me. Right towards me. It is in the direction of K. And that is the answer for this one. Mu naught I by 4 pi R by root 2. 1 by root 2 plus 1 by root 2 times K. To find out the net field, you just have to add up these two fields. Do we understand how I have got this? Yes or no? Everyone understands this?
Yes, sir.
This was a magnetic field. Due to this, I'll give you one more small question. Do it fast. I cannot give you so much of time which I given you this time around. I just gave you because I just wanted you to attempt them. Question number 2 or 3 or 4, whatever it is. This is a circular, no, not a circular. This is a square wire. Square wire. The center of the square is O. The length of the square is I. The length of the square is A and the current is I. You have to find out the magnetic field at the center of this wire. At the center of the square, not the wire. I'll give you 2 minutes to give me the answer for this one. Do it fast. If you're not able to do it, please let me know so that I can move ahead. So how are we supposed to do this? We understand all the wires are same and we just have to see whether the field is getting added or subtracted. So if I find the field due to the lower wire, the field is coming out. Due to the side wire, field is coming out. All the fields are coming out. So basically I just have to find the field due to one wire and multiply it by 4. I will just find it out for this wire which is lying here. I will have to find out this angle. I don't have to find out this angle because it is already 45 because this is a square. Yes or no? Yes or no?
Sir.
I just have to find out the value of this perpendicular. I don't have to find out because this is also a by 2. Yes or no? Because the total length is a. So what is the magnetic field? The net magnetic field B net vectorly mu naught I by 4 pi, distance is a by 2, multiplied by 1 by root 2 plus 1 by root 2. This is the magnetic field due to one wire. I have to multiply it by 4 and the direction is K. That is the answer that you are going to get. We understand this? Yes or no? Anyone got this answer?
Yes, sir.
Congratulations then. You have got this answer. So heartiest congratulations. That will bring us to the next point, next part, which is magnetic field due to a circular loop or ring of wire. Have we noted this down, everyone?
Yes, sir.
Pakka na?
Pakka, sir.
Otherwise, I'll just move ahead and then I will see, sir. Please wait. No, na?
No, sir.
Okay. So we come to the next one. Magnetic field B due to a loop. And right now we are concentrated at the center of the loop, not anywhere else. Magnetic field due to a loop, at which point just at the center of the loop, we don't have to worry much about the other points. The other point is point on the axis of the loop. We will deal with it when we come tomorrow, maybe. This is a circular loop. It carries current in the clockwise sense, I, and you have to find out the magnetic field at the center of the loop. You just have to remember the standard result. What is the standard result for this one? Magnetic field will be mu naught I by 2R. Mu naught I by 2R. That is the standard result that you will have to remember for this loop. Now remember, we have assumed that there are only one turn in the loop. There could be number of turns in the loop. If there are number of turns in the loop, then the magnetic field becomes mu naught Ni by 2R, where what does N stand for, my dear friends? N stands for the number of loops or number of turns in the loop. Do we understand this, or this has gone above our head saying bye bye?
Understood, sir.
You just have to remember this. This is only the magnetic field magnitude. What is the direction? I mean, you can find out the direction by the right hand thumb rule, or here it is more simpler. You just turn your fingers in the direction of current. You can call it right hand cock rule. All are right hand thumb rule in different ways. Right hand cock rule. So the current is going clockwise. Ding 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 ding. So you turn your curl your fingers in the clockwise sense, and where is your thumb pointing? Your thumb is pointing into the board, and therefore the magnetic field is going into the board. Do we understand this? Cock rule, wee, screw rule, wee, wee. We understand this? Huh? It has gone up above our saying bye bye. Bye bye.
Understood, sir.
Pakka, sir?
Akka, sir.
Your pakka is dangerous. Scared of your pakka. Now, have you noted this down? Let me just put it here only. Have you noted this down? Yes or no? Huh?
Yes, sir.
If you don't have a full loop, if you just have an arc of a circle, everyone has noted this down? Otherwise, I'll move forward and then say, sir, please back, sir. Magnetic field due to an arc of a circle. Again, standard result. Just have to remember these standard results and make merry. Merry. Arc of the loop. This arc of this gentleman loop is, as you can see, making an angle theta. This theta has to be in radians. This theta has to be in radians. Then we have this general formula for the arc of a loop, and the general formula for arc of a loop is mu naught I by 4 pi r. Remember this 4 pi r? It also came in the wire. 4 pi r, mu naught I by 4 pi r, mu naught I by 4 pi r, mu naught I by 4 pi r. In the long wire, it was sine theta 1 plus sine theta 2. There were two thetas. Here only one theta. For a wire theta, loop theta, sine theta will not come. Only legendary theta will come. And remember, this legendary theta has to be in which unit? Huh? It has to be in radians. And this becomes the formula, the general formula for magnetic field due to any loop of any angle. The angle has to be put in radians though. Do we understand this, or this has gone above our head saying bye bye? Bye bye. I'm
Understood,
going
sir.
bye bye. I had enough of this. I'm going bye bye.
Understood, sir.
Then if you have a semicircular loop of wire, you just don't have to worry. Just put theta as pi and you will get the result for this wire. What is the result for this wire? Mu naught I by 4 pi r multiplied by the angle pi, and you get the revolutionary legendary result. But wait. This is only the magnitude of field. How do I get the direction of magnetic field? Again, that cock rule. That cock rule. You turn your finger in the direction of the cock. Shui, like this. And then you get the direction of magnetic field. Whenever you see clockwise current, it is inside. Clockwise current is inside. Do we understand this? Yes or no? Yes or no?
Yes, sir.
In fact, sir, this formula, sir, is also derived from that formula, because this is nothing but B is equal to mu naught I by 4 pi r multiplied by the total angle is 2 pi. Do we understand this? This is gonna Baba at saying bye bye, bye bye, bye bye. I'm going, bye bye.
Understood, sir.
All these formulae have come from this simple revolutionary formula, and that simple revolutionary formula is mu naught I by 4 pi r multiplied by the angle phi. Noted this down? Yes or no? No, yes?
Yes, sir.
Just one more thing regarding the directions. I don't know, I get worried about the direction. Students always get the wrong direction for magnetic field, and if you get the wrong direction, you will never get the right answer. So this is again just a reminder of what will be the direction of magnetic field created by a wire if it is going up. Do you see? Do you understand what is drawn here? Magnetic field is moving circle, ding 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 ding. Do you understand this? Yes or no? Huh? You understand the direction of current? The direction of magnetic field.
Yes, sir.
And then now this is what we have seen. We the loop. That cock rule. We. You understand this? Huh?
Yes, sir.
Pakka na sir?
Pakka, sir.
Pakka is very dangerous. Pakka gets me into trouble. Have you noted this down? Then you can do some standard cases, and these are all questions, but I'm not giving them as questions. I'm giving them as questions which have answers given. Have you noted this down? Yes or no? Huh?
No, sir.
Then note it down, na sir. Why are you sitting, sir? Note it down, sir, and let me know when you are done, sir, so that I can move forward in life, sir. Okay, sir? Note it down fast. This is a sample problem. You can take it as a sample problem, or you can take it as a standard result. Here we have two coils, smaller coil, bigger coil. If they carry current in the same direction, this will be the result. Both will get added up. If they carry current in the opposite direction, they will get subtracted. No points for guessing this one. Do we understand this? So these two coils are coplanar and they are concentric. Wait, let me finish my discussion. If you have non-coplanar, and this question I have seen in a very recent JEE. So if they are non-coplanar and non-coplanar and concentric, then you can have this result. So I'm trying to put both the results together so that you can compare them and note them. Anyone can come, and then you should not see here and there that we don't know. So this one, everyone understands? So yes, you understand when they are coplanar and concentric, and then one is here and one is here. One is like this and the other one is like this. Do you understand the second figure? Yes or no? This is the best three-dimensional figure that I can draw. We understand this? Yes or no? So because of one wire, the current in this wire is like this. Magnetic field is going in the B1 direction because of this pink thing. We understand this pink thing? Yes or no? No, yes. Huh? Bye. Because of this green thing, the magnetic field is going like this. We understand this? You have 2 minutes to show your talents. So, we have seen this. Now, some cases where you will have zero magnetic field, and I'll just give those cases and then probably try to make you understand why is this zero. So cases of zero magnetic field, you can just note down these cases, and then I will try to make sense why these cases the magnetic field is zero. I will try to make sense. So let's note it down first, and then I will try to make sense of it, why it is zero. Because you can have any of these cases appear in your exam, and then you should not be found wanting. Cases where magnetic field is zero. Magnetic field is zero, and very nicely I had summed it up in these diagrams. Why is the magnetic field zero in all these cases? Now see, and listen to me very carefully. Once you understand this, you can draw this. Now you can see this wire AB is coming from infinity, then it gets broken into BC part. One is the BC upper part, one is the BC lower part. Then this goes to infinity. This is actually coming from infinity. Now, if I look at the magnetic field due to this pink wire here or pink wire here, this for this pink wire AB, this point O, the center of the circle, lies directly ahead, and for this pink wire CD, it lies directly behind. So for both of these wires, the magnetic field is zero. Do we understand this? Yes or no?
Yes, sir.
Now look at the green wire and look at the blue wire. When the green and the blue wire are semicircle, you can understand that current will be divided equally. Due to the green wire, if you move the circle, the cork, the magnetic field will go inside, and because of the blue wire, magnetic field will come outside. Both the currents are same, so they will also cancel each other out. So the net answer would be zero. Do we understand this? Do we understand this?
Yes, sir.
Okay. You might face problem in the second one. Now, second one, this pink wire and this pink wire, they are passing through the center O, so the magnetic field is zero. We understand this?
Yes, sir.
There is a small confusion that may come in this green wire and in this blue wire. Now, this green wire is shorter. Please listen to me very carefully. This green wire is shorter and the blue wire is longer. Yes or no? So green wire will have less resistance and blue wire will have more resistance. We have done a question where we have found out the current in the two wires. Yes or no? You will not remember it though. But we had done a question in electric current where we have found out the resistance, the ratio of resistance of the two wires and the ratio of current in the two wires. Yes or no? So this green wire will get more current and the blue wire will get less current. We understand this?
Yes, sir.
And the ratio of the current will be inverse ratio of resistance, and the ratio of resistance is same as the ratio of length. Yes or no? Blue wire has less current but more length. Green wire has more current but less length. When I find out the magnetic field due to a circular current, it is mu naught I by 4 pi r multiplied by angle theta. For blue wire, angle theta is more. For green wire, the angle theta is less. And this angle theta is proportional to the length, and that length is proportional to the resistance, and that resistance is inversely proportional to the current. And this magnetic field is directly proportional to the current. So basically what happens is everything cancels out each other. So the blue wire wala current ka magnetic field will cancel the green wire wale current ka magnetic field, and therefore the net answer would be 0. We understand what I have said? Current divides in inverse ratio. Blue wire has less current, green wire has more current. The ratio of the currents is inverse ratio of length, but then it again gets multiplied by their lengths, and that is why you get the net value of magnetic field as 0. We understand this?
Yes, sir.
Same thing happens in this one, same thing happens in this one, same thing happens in this one, and same thing happens in this one. So all the wires will cancel out each other. We understand this, or this has gone above what it's saying? Fine, sir. Ho gaya. Please leave.
Understood, sir.
We are done. Okay, so note them down because one of these may come, and I suspect that this one may come. I don't know why. Cube, current coming out, whee, and going out, whee, and they ask you what is the magnetic field at the center. I told you I was watching one of those YouTube lectures of some crazy fellow from years back, and he said whenever you see 0 in the answers, always mark 0 because 0 is always the answer. In this case, 0 is the answer, but you don't always mark 0 because not always 0 is the answer. That is a stupid logic. I'll give you 2 minutes to note it down. You have noted down all these cases. We'll have to go through one more formula, the magnetic field on the axis of the loop, and we'll have to solve some questions. The good thing is I have just now sent you a sheet. In that sheet, that is the sheet of your entire magnetic force and magnetic field excluding EMI. You may not solve those all questions, but there is a 3 or 4 pages sheet at the end of that sheet which is only based on this magnetic field due to different types of configuration and different networks. If I could just show you the part of that sheet that I am talking about, the sheet is already there. I've already mailed it up. If I mailed it up, it would have reached the office people, and the part of the sheet that I am talking about, the part of it is a big assignment sheet. The part of the sheet that I'm talking about is this one. I mean, this sheet consists of everything, right from your MEC to everything. The part of the sheet that I'm talking about is this one. And how do I show it to you? How do I show it to you? I shall show it in this way. Okay, the part of the sheet that I'm talking to you is this one. And this is the part that I'm talking about, the basic level. Do you see this? And there are a few questions that you can see on this sheet. This sheet is only for this drilling questions. So if you can, and there's space given to write the answer and solve it as well. So there are 20-25 questions, and if you can do them, probably one of these questions will land up in your paper. So go through this sheet. There are around 20-25 questions in this sheet. If you can see here, 25, 26, 28, 29, 30, more than that. 28 questions are there. 28 questions, one question will take hardly 2 minutes. So this is a sheet of 1 hour. If you can go through this sheet, the answers are given. This is the main sheet which has 256 questions. I don't think you have time to solve that, but at least you can do that assignment wala part. And that is good enough to solve this. The other part of the sheet is for the entire chapter. The entire chapter means it has a lot of things starting from all this Biot Savart law and this and that and hanky and panky and everything is there. So if you can solve them, well done. Your topic is over. So I'll give you that as an assignment, and instead of writing questions here, probably I'll straight away take that sheet and tell you the answer of those questions from there. So probably we'll do that so that we can do some questions quickly. So do them at home. It's already there. Ask office people to give it to you, and you should get it. So I'll see you in the next class tomorrow, and I hope that you complete that 23 question that I showed. Yes. Yes.
Telegram, I have sent one question, sir.
I did not get. Send it again. Okay, send it again. I'll. I did not get anything. Send it again. Okay, I will see it and I will tell you how to solve it. Or you can ask it in the class tomorrow before the class. You can send it to me and I'll tell you how to solve it in the class only. Okay. When the class, send it to me. Okay. Anything else?
Yes, sir.
Take care and God bless you, and do that sheet that I have sent you. Bye.
Okay, sir.